If you had an existing technology, proven for more than 50 years of reliable service, you certainly wouldn't try to change it, would you? I mean, if you had technology that worked, the last thing you'd do is try to fix what isn't broken. But what if you could take the strongest parts of that proven design, combine them with a new application of other proven technology, and arrive with results exponentially more accurate and complete? Results that drive scientific discovery. Results that bring profit. Results delivered in a form factor that's even more rugged and reliable. Now that would be progress. That's what we've done here at Silicon Audio. We tip our hats to the venerable seismic sensor, known as the geophone, that has been so valuable to industry for more than 5 decades. With its simple, reliable design, the geophone has empowered and enabled a multiplicity of industries which rely on geological surveys to achieve their goals. But as we are also committed to forward progress, we stepped back and took the opportunity to consider this seismic sensor design in a whole new light. And by light, we mean laser light. You see, the traditional geophone works like this. It's got mass in it, and it's got floppy springs. When there's movement, the mass suspended on these springs moves, and these coils respond to that movement, inducing electric voltage to come out as usable signals. These signals are then sent to a ground station where scientists can do a bunch of fancy processing with this data, which tells them information about what's happening underground. However, this time-tested workhorse has some serious limitations. You see, geophone sensors have a limited response range that appears like a V when charted on a graph, like this. This line shows the clip level here, where the sensor becomes overloaded, and this line represents the noise floor, or lowest readable noise frequency. So here's the usable range for a geophone. A geophone is very sensitive at its resonant frequency, but in other frequencies it tends to get noisier, and that doesn't provide high fidelity or a wide dynamic range in the data that you're trying to collect. This means you're effectively missing a large portion of the overall frequency spectrum, and that's not ideal. In the past, field users would mitigate this limitation by simultaneously using a range of instruments, maybe a geophone plus a scientific instrument or multiple scientific-grade instruments to try and cover the entire intended range. But this adds complication, expense, and additional work. And scientific-grade instruments have their limitations too. For instance, scientific-grade sensors are easily overloaded by thumping and tend to clip, meaning that they can't return clean or complete data surrounding that overloading event. This is a severe limitation. They're expensive too, and prone to breaking. Not what you want in the middle of a critical geological survey. What's more is that due to their antiquated designs, neither the geophone nor scientific-grade sensors with their dependence on very sensitive springs can take accurate readings at low noise levels unless they're set almost perfectly upright or on their side. This severely limits their use in challenging real-world applications. So, while the core design of the traditional geophone is a fantastic, reliable machine that's been used for decades, we know that certain elements of its design create less than ideal limitations. So what we said is, let's not reinvent the wheel. Let's keep the great parts that are proven to work and only change the factors that are causing these limitations. That's why all the physical, moving parts of our sensor use the same technology as the time-tested geophone. But we discovered a different way to look into and communicate our data, through the use of laser optics and an interferometer, allowing us to produce a very wide dynamic range sensor while supporting an omnidirectional, rugged, and reliable form factor. Rather than using the geophone's traditional voltage out via magnetic coils method, we're going to integrate something called an interferometer, which uses proven laser optics technology to capture seismic data. An interferometer works like this. We use laser optics to generate a beam of light, which we then split, causing the light to travel along 2 distinct paths. On one path, which we'll call the reference path, we have fixed mirrors, which are not responsive to outside motion to reflect that beam of light back at a consistent, known distance. The second path, which we'll call the dynamic path, travels along and is bounced off a motion-responsive mirror, which is mounted on a firm spring. Because this mirror moves in response to Earth movements, the distance that this reflected dynamic light must travel is not consistent. When these 2 paths recombine, the resulting light intensity changes with the intensity of each movement. The differences in distance traveled by the two split beams of light can be sensed and measured using what are called photodiodes. The resulting readouts indicate the intensity of the movements registered. So that's at the core of what our technology does. And with it, we can sense motion as small as 1 femtometer, which is really small. And we can sense the motion very easily, allowing us to have a flat noise floor and a very wide dynamic range. And since our dynamic laser optics design utilizes a stiff spring as opposed to the floppy springs design of the geophone, our sensors can be used in virtually any orientation, up, down, side to side, and any angle in between. The applications of this omnidirectional sensor are varied. Ocean floor and ROV deployed marine surveys? Yep. Rough, uneven terrain? Uh-huh. So there we go. Silicon Audio simply took what has proven to work and made it work exponentially better. We'd call that progress, right? Simple, reliable, omnidirectional, and rugged. Designed to provide exponentially more complete data in even the most challenging environments. We are Silicon Audio. Progress applied.